Hello, this is the second part of the chapter 6.1, and we will talk about the distances in n-dimensional space Rn and how to measure them. First, in the previous part, we talked about the distance of the single vectors, but we actually can easily use the similar approach to measure the distance between two vectors. It will be just, we can subtract one vector from another and calculate the length of this resultant vector. And let me show a little demonstration of this kind of vectors in R2 in a two-dimensional space. Let's say we have two vectors, u and v, and we're trying to measure the distance between these two vectors. So in other words, we're trying to subtract vector v from u and measure the length of resultant vector. And again, since we are subtracting v from u, it will be the same as adding the negative vector v, isn't it? So all we have to do now, so we have this negative v vector, all we have to do is to shift it, that it would start at the end of vector u over there, and then use parallelogram rule to find vector u minus v, something like this. So we post the minus v vector over here. So resulting u minus v vector is this blue vector over here. All we need to do is just take a ruler and measure its length, which is really easy to do in two dimensions, but much harder to do when we have a 3, 4, 5, and sometimes 5,000 components in each single vector. Let's try to come up with methodology for measuring the distance between the vectors. And again, let's start with R3. So let's try to develop general formula for distance between two vectors in R3. So we have vector u, which has three components, u1, u2, and u3, and we have vector v also with the three components. Okay, so let's try to use our distance formula, which tells us that this is just the length of the vector u minus v. Or we can write it down using the dot product of vector u minus v to itself. So we can then use our components, because our dot product to itself will be a sum of first component of vector u minus first component of vector v squared, second component of vector u minus second component of vector v squared, and so on so far. So that's a formula for 3 dimensions, but we can expand it to as many dimensions as we need. And that would work for any vectors u and v, but more interesting case here will happen when our vectors u and v lie on perpendicular lines, like over here. Or we say that they are orthogonal, because so like basic idea of perpendicularity on the multidimensional space usually referred as orthogonality. Okay, so we have again our vector u, our vector v, and when we subtract a v from the u, we'll have like this hypotenuse basically, and its length is the what we're looking for. However, because we have right triangles over here, that length will be exactly the same as we actually using vector minus v instead of v. So we subtract vector minus v from u, and we should get exactly the same hypotenuse. How that can happen? Let's try to run through calculations. Let's start from the left difference, vector u minus v. So again, we will expand it using the length formula. And if we drop the parentheses around minus v, we will have the actually sum of vectors u and v squared, which is again by using the dot product formula, will give us a product of two vectors. And we can try to expand it by factoring out the first sum of the vectors over here, and then actually just end up with multiplying everything and have a 4 vector dot products. So now you would notice that there is a couple of them in the middle here, which is very similar. And we know that by the property of dot products, u times v is equal the same as v times u. So, and also dot product of vector u on itself will equal u squared, or length of vector u, product v on itself is equal v squared. So we end up with this interesting formula for our left hypotenuse. Okay, let's look at our right hypotenuse over here and see what's the length of this vector. Should be the same, isn't it? And again, we use the same methodology. We take the first, we get the length of the first vector u squared, length of the second u squared, but now we have a negative terms of a dot product of double vector u times v. So that's very strange. We have two distances, two hypotenuses, which should be identical, but we have positive and negative terms in this equation, which only happen when our positive or negative terms is actually identical. Or in other words, that only can happen that dot product of our vectors u and v is equal 0. And that gives us a very important properties of orthogonal vectors or perpendicular vectors. We say that two vectors u and v in Rn are orthogonal to each other when their dot product u dot v is equal 0. And we will use this property endlessly for the rest of the class by defining the orthogonal orthogonal vectors of one which has dot product equal 0. And it's also allowed us to make a modified Pythagorean theorem, because before Pythagorean theorem only worked in a two-dimensional. We can expand it in the multidimensional space and say that the two vectors u and v are orthogonal if and only if the length of the sum of two vectors or multidimensional hypotenuse length is equal sum of the squared length of each vector u and v. Okay, now this is the time to go to the end of the chapter and try to practice using measuring the distances between two vectors.